Hi guys, today we'll be discussing the relation between electric current and electric charges. So before we go on to the current, which is the main part what we want to do today with a bunch of numericals on that, let us briefly talk about charges. And herein we'll not be discussing what is a charge, which is rather a deep topic, and I would like you guys to read a bit on it because we'll be discussing that in a live class or subsequently in a recorded thing, because it is very much required for your further lessons. So what is a charge? Leaving that apart, let us briefly go through what are the charge carriers. What are the particles which carry charge, which we say are charged. So what is the first thing which occurs to you when I ask you to name a particle which carries charge? So in fact, let me ask you to list down some particles which you may know to carry charge. I guess one of the foremost particle what you would have listed would be an electron, right? And how much charge does it carry? How much charge does it carry? It carries a charge of 1.6 into 10 power minus 19 coulombs. And it carries a negative charge. Now, why do we say that it carries a negative charge? That is just a convention given by Benjamin Franklin. So, without much going into the physics of it, he just chose to give it a negative charge, and it doesn't matter in our calculations. So, yeah, had it been given as a positive charge, maybe your theory learning would have become a bit easier, but doesn't matter with the progress in physics. So you may blame Benjamin Franklin for it. And a very interesting experiment he did, the kite experiment. You can rather Google it and learn about the kite experiment. There is text supporting that he did that experiment. So it's a very interesting experiment, which in those times, I'm talking about the 1700s. So in 1700s, they didn't even know that the lightning what is happening is same as the electrical phenomena what they have figured out on earth, so being on the ground. So this guy proved through his experiment by bringing the lightning down using a kite and the string. He brought the lightning down and he showed that the phenomena which is related to the electricity and the charges what they were studying in their labs, that is same as the phenomena was displayed by lightning. So American guy doing a very adventurous experiment, and there were other people before him, I guess, who had done a similar kind of experiment, and one of them had lost their life. So that most of the experiments were happening in Europe. Now this minus, the story behind the minus, I told you, it's just a convention chosen by Benjamin Franklin. And so don't worry about why electrons are negative. Electrons have a certain property of charge. What are charges? We need to know that. So I'm not discussing that. So charges exhibit a certain property. Electrons exhibit a certain property which is opposed to what protons exhibit. So one of them would be called as positive and the other one would be called as negative. So electrons were chosen to be called negative. So the other one, as I said, is proton. Proton is also a particle which carries charge. How much is that? That is exactly the same, 1.6 into 10 power minus 19. By the way, it's 1.602 something to be more precise, but we'll rather do with this value. This is good enough for us. So many coulombs, and this time it's a positive. This one electron charge or one proton charge is called an elementary charge. It's called an elementary charge. And then there are charge carriers which carry fractional charges but don't exist independently. Those are called quarks, and you don't have to bother about them at all. So the particles which we know, which is in the syllabus currently and subsequently for the next 2-3 years, are these particles: an electron and a proton And then obviously ions, you have ions. So ions can be your cations, which are positive, say in red, and your anions, which are negative. So basically, what are ions? Ions are atoms which don't have equal number of protons and electrons. If you have excess of proton or say dearth of electrons, then those are called cations. That would be say Na plus, K plus, H plus, Cu2 plus. There are various cations. So what are these? Like, what is Na? It has got 11 protons, but only 10 electrons are there, hence it is a Na plus. Had it been 11 electrons also in the shells, 2, 8 and 1, then it would have been a complete atom. Your Na is having 11 protons, 12 neutrons, and then electrons around 2, 8 and 1, which makes up 11 electrons. So you have 11 plus and 11 negative. But if I remove one of the electrons, one electron is gone, you have 11 plus and 10 negative, makes it 1 positive. 11 plus and negative 10 is effectively 1 positive, that's an ion. So if you have a disbalance of number of protons and electrons in an atom, that creates an ion. So if you have excess of electrons, so excess of electron comes when the atom is ready to accept. So this Na won't be ready to accept, because as such this is not a complete shell. Atoms which are having almost 8 electrons in the outermost shell want to make it up as 8, say 7 or 6 electrons in the outermost shell, will take in an electron or take in 2 electrons and become an anion. So some examples of anions: Cl minus, hydroxyl ion, sulfate. These are anions. So these are big fat charge carriers because effectively they are having that extra electron on it. So electron is a basic charge carrier. This is having an extra electron on the whole bulk of Cl. And this H plus, mind you, H plus is nothing but the proton itself. Because what is H? What is H? H is one proton and around it one electron. If you remove that electron, it is just the proton left. So H plus is nothing but proton. So these are the charge carriers what we'll have in our course. And what can you tell me about the charges they carry? What will Na plus carry? It will carry one extra proton. So the charge on it will be 1.6 into 10 power minus 19 coulombs. Same for this, twice of that much. So that will be 3.2 into 10 power minus 19 coulomb for your copper 2 plus cupric ion. And then chloride and hydroxyl will have a negative 1.6 into 10 power minus 19. So it is 1 electron negative, and this is twice of that negative. So these are the ions which can carry charge. And where would ions carry charge? Ions would be in a solution. They would be in an aqueous solution, and that aqueous solution would be called an electrolyte if it is carrying charges. So that also is in your chemistry course, where you'll have some ions carrying charges. And then what else can we discuss which is within our scope? Maybe say alpha particles, beta particles. What are alpha particles? Alpha particles are nothing but a helium nucleus. The electrons have been removed and it is just the nucleus. So what was helium? Helium had 2 protons and 2 neutrons. Neutrons don't have any charge. Just the protons have a charge. And then it had 2 electrons around it, but those 2 electrons have been removed. There were 2 electrons around it. That's a helium atom. If both the 2 electrons are removed, then only 2 protons, 2 neutrons remain, only the nucleus remain. So that is your alpha particle. So it is also written as alpha, the symbol is alpha, can also be written as helium 2 plus. because that's a helium ion. So when I'm talking about alpha particle, I'm talking about a cation of helium 2 plus. Now what is beta particle? Similarly, beta, the symbol of beta is this, but basically it is nothing but an electron. So generally we talk about alpha particles and beta particles when nuclear phenomena are happening. That means an electron is getting shot out of the nucleus of some atom. We say a beta ray has come out. So anyways, if these things are moving, then that is going to constitute a current. So hence we are talking about these things. Now another thing I would like to comment on is the unit of charge. What is the unit of charge? What is that C? That is coulombs. That is C is coulomb, and all units by convention is written in, starts with a small letter, even though it is after the name of a scientist, Charles Augustin de Coulomb, a French guy. So mostly these French people were doing a lot of experiments in those times, again in 1700s. So just to honor him, the unit, SI unit, was named after him as Coulomb. You'll be doing Coulomb's law in class 11, wherein you'll know how much of work he has done with what is the effect of charge around it. So what is the electric field around a charge, that kind of work you'll be studying about Coulomb. So the unit was named after him. That is in 1900. The guy would have died in some 1800. That's after 100 years the honor was given. So basically these are the charge carriers about which we'll be talking about, the movement of which we'll be talking. So let us come to the word electric current. I hope you have noted down this thing. Elementary charge, by the way, is called E. So a electron is having a charge of a minus 1e, and a proton has a charge of E. So even though E is a letter which depicts that it's the electron charge, but the electron has a minus E charge and a proton has a plus E charge. E is a positive quantity. It is plus 1.6 into 10 power minus 19 coulombs. And all charge particles will come in multiples of E's, that elementary charge. You have nothing which is a fraction of E which exists as independently. I said cork is having a fraction of E, but that doesn't exist independently. So any particle which is charged, say you have taken a balloon and you have rubbed it on your shirt, then it is carrying some charge, because either it has shed away some electrons or it has taken some electrons. I think you would have done those experiments by rubbing the balloon on the shirt and then sticking it on the wall. So that happens because it gets charged. Now that charge will be a multiple of this. Any charge would be a multiple of this, and it's such a tiny quantity that the charged particles, what we generally deal with, would almost seem to gain charges very smoothly and not in steps. Gain or lose charges very smoothly and not in steps. So any charged particle has got a charge in multiple of this. That is called quantization of charge. The term is called quantization of charge. So let me just clear the board and ask you a few stuff on that. Hi, now since I mentioned elementary charges, let us talk a bit on quantization of charge. As I was mentioning, the charges will not come in fractions of E, that elementary charge. It would be in integral multiples of E, either 1E, 2E, 1000 E, or million E's, but it won't be a 1,000,000 E, it won't be a 2.5 E, it won't be a 2 1/3 E, or a minus E. A minus E is carried by an electron, a plus E is carried by a proton. That's the elementary charge. So I'll just list down few charges and do let me know what do you think, whether these charges, this amount of charge, will exist on any body or not. Say 3.2 into 10 power minus 19 coulombs, plus or minus. Plus would be carried by the protons, negative would be carried by the electrons, and they are the same amount, they are the same value. That's a plus E, this one is a plus E, and that's a minus E. then a plus or a minus 0. Say 4 into 10 power minus 19. Will anything carry this much of charge or not? Will anything carry 0.8 into 10 power minus 18 coulombs or not? So do let me know what you think, whether these charges are possible or not, and a bit of discussion on, say, plus or minus 0.001 coulomb. When we are talking about something which carries this, whether this charge on something is possible or not. Yeah, I hope you have given an answer. Clearly we can see this is twice of E, so this is equal to 2 times E. E is the elementary charge, so this is very much possible because 2 is an integral number. That if it is plus, then it is made up of 2 protons. If it is a minus, then it is made up of 2 electrons, or it is having 2 extra electrons than the number of protons in it. Now what about this one? 0.4 into 10 power minus 19. How much of an E is it? How much of an E is it? It is 1/4 of an E, which is not possible. That is not possible. You can't have a fraction of a E. You can have 2 E's, you can have 10 E's, you can have a billion E's, but you can't have a fraction of an E. Now what about this? I hope you have got the catch over here. It is 10 power minus 18 mentioned. So you can rather write it in 10 power minus 19 as plus or minus 8 into 10 power minus 19. So we have made it 10 power minus 19 as these were, and then we'll compare with the E. So how much of an E will make it 1.6? We are assuming that this is a precise value. There are bit of other decimal places and decimal numbers after this, but we are not going into that precision. So provided this is the precise value, how much would this be, or how much would this be? That's a 5 times E. That's a 5 times E, because it's 8 into 10 power minus 19. So don't think it was a decimal, but then there was extra 10 in it than the 10 power minus 19. There's extra 10 in it, so that is 5 times E, and this is very much possible. Now to discuss about this, now technically maybe this is not possible, but then in physics, if we have written the answer till here, if we have written the value of something till 3 decimal places, we don't assume that the rest is all 0. This is the significant number, and then there might be other numbers in front of it. Right after 1, there may be a 1.0011, and you just mentioned till 3 decimal places, and hence you mentioned only this. Maybe it was a 0 in front. So if you are sure it is a 0 in front, you'll rather mention that while you were giving that value, if you were sure it is 0. So if you are not sure, then you don't mention that 0. So if it was not mentioned, we don't know whether it is a 0 over here or not, and whether it was a 0 over here or not, it won't matter much, because ultimately if I have to see that how much multiples of the elementary charge is this, then an extra E or one less E is going to make a difference after 19 zeros. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19. So here is where the difference will come. So if the question asked is whether this charge 0.001 charge is that possible or not, then you will not say that this thing is not an integral multiple of E, because the integral multiple is going to make a difference over here after so many zeros. So this mentioned amount doesn't mean that so many zeros is following it. It doesn't mean so many zeros are following it. If this is the mentioned amount, then maybe some numbers are over here which is never mentioned, because nobody writes all the numbers. Nobody is going to write all the numbers, and this is what significantly is mentioned. So meaning to say, if you are talking about charges, the real life charges like a coulomb or a 0.1 coulomb or a 0.001 coulomb, or even many zeros and 1 coulomb, these are all possible charges, because an extra E or a less E is going to make a difference after many zeros. So if they ask you, is this a possible charge? Yes, this is a possible charge, and you don't have to actually see whether it is a multiple of E or not. You are going to check whether a given charge is a multiple of E or not when they are mentioning charges like this, so many zeros, and then doing something over here. After 18 zeros, after 17 zeros, after 19 zeros, they are giving some numbers. Then you will have to go into the precision. So mentioning a 10 power minus 19 or 10 power minus 18 is telling you that we are going for so many zeros. So this question in fact would be what? It would be 0.8 divided by 10 power 18. So that means it would be 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18 and a 8. This one is this. So if they have mentioned this, whether this is possible or not, then you are going to check out that here it comes as an integral multiple of E or not. If they have mentioned these kind of things and so many zeros are not mentioned, then you don't have to bother about it. So these are all valid questions, and this you would straight away say that this is too large a number, and the electron, one extra electron or one extra proton makes a difference after many decimal places. So this one is very much possible. So this is what is quantization of charge. Mind you, since charge comes in integral numbers of E, since it is quantized, that was the reason why we were able to find this value. So you can read Milken's oil drop experiment, where the basic reason of him able to figure out how much is the charge was that the charge on the oil drops, the tiny mist of oil which is formed, the charge on that would be in integral multiples of a certain number. It was jumping in certain numbers, either this charge or the next one or the next one, nothing in between. So since that basic thing was known, that integral multiple, Milken was able to find out how much is the value of an elementary charge. Hi, now that we know what are the particles which carry charge, like electrons, protons, ions, let us now discuss what is electric current. So the word current, what does the word current mean in general? If I say there is a current in the river, what does it mean? It means that water is flowing in the river. If the water is not flowing, there is no current. So current signifies a flow of something. So what would electric current signify? Electric current would be the flow of charges, the electrical charges. So these particles, which were the charge carriers, if they are moving, then that constitutes electric current. More charges are flowing, more would be the electric current. So before going ahead, let me ask you one thing. If I say 10 coulombs of charge has flown through a certain point, it has gone past a certain region, and if I say 1 coulomb has gone past a similar region, which is constituting more current, then is this information which I gave you is enough to answer the question or not? I'll repeat the question. The question is, if I say 10 coulombs have gone through a certain region and 1 coulomb has gone through a similar region, which of the two cases, in both cases the charges are flowing, which of the two cases signifies more current? Is this information enough to give me an answer, for you to give me an answer? Let's see. I'll further say that this 10 coulomb has gone past a certain region in 1 minute, and this 1 coulomb has gone past a similar region in 1 second. Now, is this more informative for you to give me an appropriate answer? Yes, this is more informative. A 10 coulomb in 1 minute means 100 coulomb in 10 minutes. 100 coulomb in 10 minutes is as good as 10 coulombs in 1 minute, right? The flow would be same. If I say 10 liters is flowing down a certain pipe in 1 minute, it's same as saying 100 liters is flowing down in 10 minutes. Per minute 10 liter. Another minute, another 10 liters, another minute, another 10 liters, and in 10 minutes, 100 liters. So just the amount of charge which is going is not enough, but in how much time it is going to tell you how massive is the flow. This number, a big number like 100, doesn't mean that the flow is more unless until this big number is happening in the same time. If this big number is happening in big time, like 10 minutes, then 10 coulomb in 1 minute is as good as 100 coulomb in 10 minutes. So just saying that a certain charge has gone past is not enough, but in how much time it has gone past. So let me see. 10 coulombs in 1 minute means in 1 second it is 10 divided by 60 coulombs per second, right? In 1 second it is 10 divided by 60 coulombs. So since I mentioned the second over here, 10 divided by 60, which is 1 by 6 coulombs. And this was 1 coulomb in 1 second. So in 1 second, it was 1 coulomb. So this was a greater flow. This is 1 by 6 of a coulomb, and this is 1 coulomb. So this was a bigger flow. So the point over here is not only the amount of charge which is going, but in how much time it is going is important. So the current is in fact the rate of flow of charge. Rate of flow of charge. Rate of flow of charge. It is electric charge, by the way, over here. So this rate of flow tells you how much is the current. What do you mean by rate? What is the rate of distance covered? That's speed. Rate means per unit time. Rate of water flowing would be something like liters per second, liters per minute, liters per hour. Rate means per unit time. Rate of doing work done per day, per year, or whatever. So rate means per unit time. So your electric current is defined as rate of flow of charge. So you can write down the definition. By the way, I'll give you a twist in the definition a bit later. When we are doing electromagnetism, then we'll understand that in fact current is taken as more fundamental than charge, and hence we should not be defining current using charge. But for now we are defining electric current using charge. So rate of flow of charge is your electric current. That's the definition. So you may write it down. Electric current is defined as a rate of flow of charge. Now in SI units, you'll take the charge in coulombs and time in seconds, and we can write a formula for it. Say electric current is depicted by the letter I. Then I is equal to Q by T, where Q is your electric charge and T is the time in which it is flowing. Yeah, so you can write, I'll just repeat, electric current is defined as the rate of flow of charge across a certain point or a certain region. How much charge is going across a point or a certain region in how much time. So you can add to the definition across a point or through a point or past a point or a region. So if I'm going for the SI units, then I'll take the SI unit of charge, which is coulombs, and for time, which is second, and you'll get your current having a unit of coulomb per second, which is called ampere. As I said, fundamental is ampere, and coulomb should be defined as ampere into second, but that is a story for later, and we'll do it later on, but not in this class and not in this lesson. So in this lesson, what we are learning is, we are learning current as rate of flow of charge. So charge per unit time is defining your current, and ampere is going to be defined as coulomb per unit time, second. So coulomb per second, that's your ampere. From where is the word coming? Ampere, again a French physicist, mathematician, André Marie Ampere. So you can Google that and read a bit. These guys have done. He was in fact the father of electromagnetism. Electromagnetism was called electrodynamics those days, So again the same era, a bit later after Coulomb. After him it was later 1700s and early 1800, when this guy did a lot of work and built a lot of devices. I think telegraphs and all was built by him. So this guy Ampere, to honor him, current unit has been called as ampere, and that's ampere. You will notice again that I'll start it with a small a. The guy's name is with a capital A. The unit is called ampere with a small a, and the letter which depicts the unit is a capital A. So mind you, these are the conventions what we use, and this is how ampere is written, not with a capital A, with a small a. Then the abbreviation is having capital A in it. So ampere is equal to Coulomb per second. So shall we do few questions on this based on this formula? I hope you have understood this. The first one would be, let me just clear the board for you. Okay, so these are the questions. You have 12 Coulomb charge flowing across a certain point in 1 minute. So say all of these except for the last one where I have written left to right and all, say all of these, the charges, the mentioned charges are going from left to right. So what I need you to find out is how much is the current and what is the direction of the current. So I have not commented on the direction of the current yet, but I'll want you to answer that first. So 12 Coulomb charge flows across a certain point 1 minute is your first question. Then 12 Coulomb charge is because of some particles which are charged. So let us talk about the particles. So there is a charged particle like helium 2+, which is called an alpha particle. 10 part 20 of these, if I'm going to get to a certain particle like an atom, then I have to have a massive collection of that so that it is a substantial amount. So it is the charge is a substantial number. So a 10 part 20 of the alpha particles goes across a certain point in 80 seconds. So there's alpha beam, alpha ray, which is going across a certain point, and so many passes a certain region or a certain cross section in 80 seconds. So there, what is the effective current? What is the current due to this flow? The next one, instead of writing a massive number like that, we know that 1 mole is a big number. It's 6.022 into 10 power 23. But just for rough calculations, we'll just ditch that 0.022 and we'll say 6 into 10 power 23 is 1 mole roughly. So 0.3 moles of electrons. 0.3 moles of electrons, where 1 mole means so much. So the unit mole is written as MOL and the whole thing is pronounced as moles. So moles of electron or mole electron, MOL electrons I could have written in 10 hours. So 0.3 moles, it's a big number. Even though it's a decimal in moles, mole itself is a massive number, and in chemistry we'll be doing that how big a number it is. But the question over here right now is 0.3 moles flows across a certain point of electrons, flows across a certain point in 10 hours. And now, so it is very similar to that. Instead of giving you the number exactly, we are saying how many moles. So you have to find the effective charge, and then to get the rate of flow, that charge by time is going to give you the current. And this one, again the charge carrier this time are ions, copper 2+ ion and sulfate ion. So 0.15 mole of copper 2+ is flowing from left to right, and 0.15 moles of sulfate is flowing from right to left. So it is going, so the drawing is made over here. Copper ions in the electrolyte in an electrolytic solution. So that's your electrolytic solution. In a solution, I hope you know that electrolytic solution, or simply a salt solution, it passes on electricity. So what is carrying that electricity? What is carrying the how the charge is flowing? So that electrons or protons, they are not independent. They are with a whole bunch of other electrons and protons around it. That is called a whole ion. So the whole ion flows. So like here in sulfate, I can say 2 electrons are piggybanking on that sulfate SO4 and it is going through, it is flowing. So obviously it will be more sluggish, the flow will be more sluggish than only electron flowing, because only electrons are light. So a conductor like a wire and all, the electrons, the free electrons just flows much faster than what an ion will do. But anyhow, the ion is carrying the charge. Sulfate is going towards the left, copper 2 plus is going towards the right. And what is the effective current due to copper, due to sulfate, and the net current? And the net current is how much? So due to copper, how much is the current in what direction? Due to sulfate, how much is the current in what direction? And what is the net current? So just do these 4 questions and we'll discuss that one by one. I really hope that you get all of them right. So take your time, pause the video, and once you are done, you just fill in the answer and then we'll check. And mind you, don't get into the mind frame of saying that I don't know moles, how can I do it? So the number how 6 into 10 power 23 came, 1 mole is equal to that much, is not important. If I say 1 dozen electron is going past a certain point, then in so much time, then how much is the current? You can't say that I don't know what is, how they found out what is dozen and all. What we know is dozen means 12. Why it was named dozen and all is not our concern. So if I say 1 dozen electron is going through, means 12 electrons is going through. If I say 1 mole of electron is going through, it means 6 into 10 power 23 electrons are going through. If I say 3 dozen is going through, then it means 3 into 12 is going through. So if I have a 0.3 moles, you would know that how many electrons are going through. I don't want to comment on that. So how many electrons are going through, you have to find out by the fact which is given. You don't have to have any prior knowledge of this. In fact, it is better if you don't have any prior knowledge, and just the facts what is written on the board, you can use that and get the answer. So do get all the 4 answers, apply yourself and get it right. Best of luck. So I hope you got these right. Let's discuss the first one. It says 12 coulomb is flowing past a certain point in 1 minute, say in a wire or somewhere. So 12 coulomb per minute it is going. To get the answer in amperes, you should have the charge in coulombs and the time in seconds, and we can apply this formula to get the current. So the current, capital I or small I, is how it is denoted. So say capital I write is equal to the charge. How much is the charge? That is 12 coulombs divided by time in second. How much is that? That's 1 minute, but 1 minute will not give you, 1 minute is not going to give you the SI unit. The answer is absolutely right. The answer is 12 by 1 coulomb per minute, but coulomb per minute is not ampere. Coulomb per second is ampere. So I'll rather convert this minute into seconds. So that becomes 12 coulomb by 60 seconds. Mind you, whenever I'm writing values in a physics formula, I always write the units. Without the units, it doesn't make sense. So sometimes you just write the number when you are in a haste, but the correct way is always writing the units. That is how you get a better hold of what you are doing. So your answer is 12 by 60, which is 2 by 10, which is 0.2 coulomb per second, which is called ampere. That's your first answer. I hope you got that right. Now the next one, again we have to apply the same formula. Not a big deal at all. You have charge divided by time. How much is the time given? It's given 80 seconds, so no conversions required over there. And then you have been given the charge in a bit of fancy terms, which is 10 power 20 helium 2 plus ions, 10 power 20 alpha particles. So let us see what is the charge carried by 1 alpha particle. 1 He2 plus is having a charge of 2e, where E is the elementary charge. It is having the charge of 2 protons. I already told you in the previous frames that 1 helium is made up of 2 protons, 2 neutrons and 2 electrons. 2 electrons removed, just 2 protons remains which carry the charges. So the charge is of 2 protonic charge, which is 2e, where E is equal to 1.6 into 10 power minus 19 coulomb. So it is 2 into 1.6 into 10 power minus 19 coulomb. I have no hurry to multiply because this is not the final calculation. No need to write it as 3.2 into 10 power minus 19 because I have to put it into further calculations. It is better, it is broken into factors, it is better for my calculations. So I'm not going to multiply yet. So that is the charge carried by 1 He. Do we have 1 He2 plus? That's a charge carried by 1 He2 plus, 1 alpha particle. But we don't have 1 alpha particle, we have 10 power 20 alpha particle. It's like zillions and zillions. It's a very, 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 very large number. It is a number beyond our imaginations. It's a very large number. So 10 power 20 alpha particles would be how much charge? 1 alpha particle is so much charge. 10 power 20 would be 10 power 20 into so much, which is equal to 10 power 20 into 2 into 1.6 into 10 power minus 19 coulombs. So that's the charge, that's the Q divided by, that's the total charge what you are having. So here you see a 10 power minus 19 and a 10 power 20, so you'll get a decent charge, some coulombs divided by 80 seconds. So do we have a coulomb by second? Yes, we have a coulomb by second, which will be called as ampere. And if you do the calculations, what do you get? You can cancel a 2 over here, and a 10 power 20 into 10 power minus 19 is effectively 10. So 1.6 into 10 will become 16. So that's 16. So you have a 2, you have a 16, and you have a 80 amperes. That's your answer. So you can figure out how much it is in decimal. So 8 goes with 16 and gives you a 2 over here. 2 into 2 is 4. 4 by 10. 4 by 10, that means 0.4. In fractions, you can leave it as 2 by 5. So 0.4 amps. These are the kind of amperes which actually flow in your house. Suppose you check your charger rating. So some milliamps are there. Amps, 40 milliamps, 100 milliamps. A TV and all may be drawing 2 amperes. 2 amperes is a big current. You have 6 or 7 amperes drawn by geyser or heaters. So those are big. Generally, a fraction of an ampere is what most of the equipment in your house would be using. Now the next question, I hope you have got this right. So what was the catch over here? What was the key over here? You have to get your Q right. You have to get the total charge right. The total charge was number of particles into charge carried by each particle. So here number of particle in this particular question was 10 power 20, and the charge carried by each particle was 2 into 1.6 into 10 power minus 19 coulombs. Next question, question number 3. Again, let us get our ingredient over here, that is Q and T. Q in the correct units of coulombs and time in the correct units in seconds. So the easy one first, how much is the time given? It's given that 0.3 moles of electrons flow past a certain point in 10 hours. So the time T is equal to 10 hours, which is not going to help me that much. Let us convert it into seconds. So 10 hours means 10 into 60 minutes into 60 seconds. So time is 36000 seconds. That is what is given. Let us just keep it like this so that we have ease in cancellation while we are doing the calculations. And let us get the charge. What is the charge given? Charge is given as 0.3 moles of electron. 0.3 moles of electron. Now 0.3 moles means how many? The number of particles are how many? Charge of the charge carrier, which is the electron, we know the charge. Charge is 1.6 into 10 power minus 19. 0.03 moles, sorry, 0.3 moles. How many are those? So since I have less space and I don't want to rub off this, let me just write it over here. Yeah, okay. So how many particles we have? We have 0.3 moles. What does a mole mean? Mole means a collection of roughly 6 into 10 power 23 anything. I can say a mole of 100 rupees note I'm having. That's like too much. I would be richer than any person in this world. In fact, combined richness of all the persons in this world would still not beat me if I have that kind of money. There's a very big number. It's not like a billion or so. It is a billion of a billion of a billion. It's a very big number. So 0.3 into 6 into 10 power 23, these many particles, these many electrons I'm having, and each electron has a charge of minus 1.6. So I'm just ignoring the minus right now over here. It's negative charge, minus 1.6 into 10 power minus 19 coulombs. So this is a total charge carried. So the total charge carried is so much. Hence the current, which I'll write over here. In fact, I'll just write over here. Current would be this number divided by, so let me write the current over here. The current will be this number divided by in how much time it is going past a certain point or a region. So this is, the time is 10 into 60 into 60 seconds. So I've got my coulomb per second. So I'll call that as ampere, and we'll do some calculations over here. We have a lot of zeros on top also. 10 power 23, 10 power minus 19. So 10 power 23 into 10 power minus 19 is going to give me 10 power 4. 10 power 23, 10 power minus 19 means 1 divided by 10 power 19. So 10 power 23 divided by 10 power 19. So 1 and 23 zeros divided by 1 and 19 zeros. So we are still left with 4 zeros. So 10 power 4 on top. So I'll just rewrite it and use those zeros to make these decimal values as proper values. So I'll use, out of the 4 extra zeros I'm having, I'll use one other zero to make it a 3. The 6 is a 6. 1.6 I'll make it a 16, so that I'm little at ease with my calculations. So I've consumed 2 zeros out of the 4 zeros I'm having. So I'm still left with 2 zeros on top. So that's a numerator divided by, the denominator is 10 and a 60 and a 60, and the whole value is so many amperes. So what we get is, we cancel a 0 and a 0, a 0, 0 here, 1 0 is still left. 1 6 straight away cancels, good for me. 1 6 straight away cancels. Then there's a 3. So 3 into 2 into 8, 16 is a 2 into 8, so which will cancel out. So 3 with 6 will give me a 2 at the bottom, which will cancel with 16 and give me a 8 on the top. So what I see I'm left with is 8 and a 10. So 8 by 10 ampere is my answer, which is equal to 0.8 amps. So I hope you got that. And then about the direction, in the first two, both here 12 coulombs is written, so it means a plus 12 coulomb going from left to right. So current is also going from left to right. The current direction is the direction of flow of positive charge. Here also alpha particles are positive charge going from left to right, so the current is left to right. So I'll just mark the direction of the current left to right, current left to right. Here the electrons, in this particular case, the electrons are flowing from left to right. If the electrons are going this way, then the current is going in the opposite direction, because electrons are negative in charge. Negative charge going from left to right is effectively positive charge going from right to left. There's no actual positive charge movement, but the effective current is obviously not the direction of flow of negative charge. It is the direction of flow of positive charge. So it is reverse of the direction of flow of negative charge, electron being negative. So the current direction becomes right to left. So here the answer is 0.8 amperes from right to left. That's your third answer. So those who are stuck with how to convert 0.3 moles of electrons into how much effective charge it is, which is 0.3 into 6 into 10 power 23 into 1.6 into 10 power minus 19, that's the effective charge, may now try out this if they have got it wrong. So you can pause the video and then come to that. In the meanwhile, I'll just clear the board. So now let us analyze this question number 4. So here what is happening is you have two charge carriers. You have copper 2 plus as well as sulfate 2 minus. So what is the charge carried by one copper 2 plus? Let's see that. Copper 2 plus. It means that from a normal copper atom, 2 electrons are short. If 2 electrons are short, means 2 protons are in excess, then the charge carried by this would be 2e charge, a plus 2e charge, which means 2 into 1.6 into 10 power minus 19 coulombs. You see, I don't write 2e coulombs. E is itself 1.6 into 10 power minus 19 coulombs. So E is having a unit. That elementary charge is a unit. So then the charge carried by copper 2 plus is so much. How many of them are there? So the total charge constituted by copper 2 plus, let me write it as QCu2 plus cupric, is equal to 0.15 moles, meaning to say 0.15 into 6 into 10 power 23 roughly. Mind you, I'm not using the exact value of the moles over here because we are doing a bit of rough calculation and just getting into the concepts of these questions. So that's the total number of copper ions given to you, and each copper ion is having 2e charge, which is 2 into 1.6 into 10 power minus 19 coulomb charge. So that's the key. I hope you've got the total charge right. So in these questions where your I is equal to Q by T, hardly they can make any difficult question. Just they can play around with the charge, they can play around with the time. So they can change the units of time and give you charge. The various variations I'm giving you can be the only complication what they can throw in. So Q is so much. So first we are wanting to find how much is the current due to copper moving from left to right, as it is given, moving from left to right. So copper 2 plus, the movement of copper direction would be the movement of the current direction because copper is a positive charge. So movement of positive charge is the current direction. So your current due to copper, I'll write a capital I because I have been using capital I all this while. So capital I copper 2 plus, current due to copper 2 plus is equal to charge of copper 2 plus, which is 1.15 into 6 into 10 power 23 into 2 into 1.6 into 10 power minus 19 coulombs. So in 10 hours these ions are moving, though so many of them are moving across a certain cross section or a certain point. So say this is the cross section, and so many copper ions are going that side, and so many sulfate ions are coming this side. So many copper ions constituting of so much charge is moving in 10 hours from left to right. So 10 hours again would be 10 into 60 into 60 seconds. So we have coulomb by second again, and we'll do the calculation. You can see that this calculation is almost same as that. Instead of a 0.3, I have a 0.15. 0.15 is half of 0.3. So I gave you similar numbers, so you don't have to calculate again and again. 0.15 is half of it, but I've got a 2 over here. So 2 into 0.15 makes a 0.3, and the rest is all same. So you may do the calculation again, but it will give you 0.8 amperes. And let me also make an arrow for the direction. It is from left to right. So it is going this way. The current is going this way. The current is going that way. That's your answer for the current constituted by copper ion in the same question, in the same electrolyte in fact. the current constituted by sulfate would be, let us figure out how much is the charge on a sulfate. Sulfate ion is 2 minus, that means it again has minus 2 elementary charge. So minus 2 electron charge, so that would be minus 2 into 1.6 into 10 power minus 19 coulombs. So how much of a charge was there on copper 2 plus, on cupric ion the same amount of charge is on sulfate but negative of that, and then same amount of sulfate, which is 0.15 mole, is going from right to left. So in fact the charge due to sulfate will be 0.15 moles into the charge carried by sulfate. So since it is negative and 0.15 mole, 0.15 into 6 into 10 power 23, those are the number of particles of sulfate, those many ions of sulfate, into the charge of each sulfate is 2 into 10 into 1.6 into 10 power minus 19. The minus I put over here. So you can see that this calculation is same as that calculation. Instead of a plus, I got a minus this time, and it is going past in the same time, which is 10 hours. So the current due to sulfate would be charge due to sulfate divided by time. So charge due to sulfate and charge due to copper was same. So what I'll get is same calculation, same time. So I'll get a 0.8 amperes again, because it is ditto same calculation. Let us look at the direction. The sulfates are going this way. It's written that it is going from right to left. So the sulfates are going this way, but sulfates are negative. Hence the current constituted by sulfate would be that way, which is left to right. So the current by sulfate is again left to right. Current by copper, cupric, was again left to right. So both of these currents get added instead of getting subtracted. They are getting added. So it is the positive particles moving this way and negative particles moving that way is giving an effective big current in the left to right direction. So it's not cancelling out. Had the positive particles moving this way and positive particles again moving that way, so some positive moving this way, some positive moving that way, would have effectively cancelled the current, and it would have been no current. But this time it is positive this way and negative that way. So it is adding up to the currents, and the total current, so the current direction by sulfate and copper are same. Both are that way. Hence the net current in this case, I, is equal to current due to both, which is equal to 0.8 plus 0.8, which is 1.6 amperes. That much is the current for question number 4. I really hope you got that right. If you haven't, then note down these, and if you have doubt in this, please jot down your doubt after going through the video. If you still have doubts, you jot it down, and we'll discuss that in the live doubt session, and you can very well post the doubt in the forum. So that is pretty much it for this formula. I is equal to Q by T, that is current is rate of flow of charge. So if the charge is flowing, it is having a certain velocity. So we have a formula in higher standards. You'll be doing a similar formula for current, where it will be related to the velocity of the charge carrier, particularly the electron. So the velocity of the electron will be constituting the current in a wire, in a conductor. So that velocity, I'll just want to discuss a few things on that velocity. Nothing related to the course, so it doesn't matter for your 10th standard, but we have a perception that the velocity of the electrons would be a very high number, would be quite fast, because as soon as I switch on a certain electrical device, how much of a far is the switch from the device, we see the effect immediately. Like if I switch on a bulb no sooner I switch it on, the bulb glows. It doesn't take a long amount of time for the current to reach there. And similarly, if you are going to switch on a fan, it just switches on the time, it just starts rotating the time you put the switch on. So what do you think is the velocity of the current? What do you think is the velocity of the current? I'll just clear the board.